This video has been supported by JLC PCB. Hey guys, last time we defied the shortage of black nitrile gloves and fought bravely against the omnipresent malicious influence of temperatures on all things precise, in spite of that handicap. Well, the shortage of gloves persists, but today we are fighting a completely different kind of omnipresent malicious influence on all things precise. Noise. We had a few brushes with noise before. It's an important metric for judging power supplies and DACs after all. But so far it used to be as easy as plugging in a scope and measuring RMS or peak-to-peak values directly. Things are not so easy anymore. Nowadays there are switching power supplies out there whose noise you can't even distinguish anymore from that of linear ones. And it gets worse. There are use cases where esoteric effects like popcorn noise in semiconductors matter. It just so happens that those are precisely the use cases that I'm interested in. I want to know how noisy my voltage references are, for example. To find out, I need a test setup whose own noise doesn't overshadow that of my device under test. In particular, it needs to be a lot less noisy than the ultra-precision voltage reference LTZ1000 in this case. Haha, good luck with that. Here's why that matters. These voltage references are usually used in analog to digital converters. If we were to equip a voltmeter with a 70 mV peak-to-peak noise Vref which we've just measured, then its least significant digits would become random and meaningless, essentially turning the meter into an equivalent of the $5 hardware store special. Nothing wrong with the $5 hardware store special, but I like my digits intact. All 8.5 of them. So back to the task at hand, low noise measurement. Naturally, I'm not the first one to be interested in this. There is, for example, Linear's application note 124 by analog virtuoso Jim Williams. He came up with a sophisticated design based on a cookie tin, containing a discrete JFET amplifier and a hermetic, low-leakage, wet tantalum slug capacitor, which would cost about $700 today. Then there are numerous designs by EEVblog forum members, where mostly modern, integrated op-amps are doing all the hard work that Jim Williams had to do by hand. Everybody agrees, though. What's needed is an 80 decibel gain preamp with a 0.1 to 10 Hz bandpass filter. That will make even the tiniest of esoteric effects visible. And we're going to get results that are directly comparable to the 0.1 to 10 Hz noise specs that are given in all respectable component datasheets. This is what 0.1 to 10 Hz is going to look like when we are done, just as a morsel of interestingness in between all of these boring screen captures. And this is why the 0.1 to 10 Hz band is the most interesting and the most important to have under control. In my design, I want to try and use a brand new chopper-stabilized operational amplifier. The ADA4523 has only just been released in May 2020, and it's an absolute low-noise champion, theoretically usable even below 0.1 Hz. With about 4 nanovolt per square root hertz in my region of interest, it would be good enough on its own. But just because I can, I'm going to use 4 of them in parallel. Averaging their outputs will only attenuate the unwanted, uncorrelated op-amp noise by almost 1/2, while leaving my measurement signal untouched. These 4 op-amps are configured for times 10,000 gain. Their amplified and averaged output signal goes into a 4th-order Sallen-Key low-pass filter, which will strip away all the high-frequency content above 10 Hz. I'm turning all that into a pretty good-looking PCB layout, if I may say so myself, with multiple options for a few critical components like the input capacitors. And JLC PCB is turning that into a picture-perfect reality. Their infamous 5 boards for $2 plus shipping offer is ideally suited for this kind of experimental project. It allows you to make improvements or correct mistakes that are guaranteed to be on every first-generation PCB ever, at negligible cost. For a simple 2-layer board like this, their service is also amazingly fast, which is in many cases even more important than a low price. I had these boards in my hands only 4 business days after uploading the files. Their 4-layer boards up to 100 by 100 mm have also gotten really cheap. So much so that I ended up with an entire catalog of future circuit board projects. Even though the board is shaped to fit inside a metallic fissure enclosure and to make electrical contact with the exposed edges, I still made an effort to fit all the sensitive high-gain circuitry underneath an additional internal shield. Speaking of the devil... Oh, whoops, never mind those. Those are destined for another circuit. My bad. Speaking of the devil, here the ADA4523s are being deployed. To not screw up the placement too much, I'm using a fantastic KiCad plugin called iBomb. It generates a single JavaScript-soaked HTML file with an interactive map of your board. As per manual PCB assembly protocol, I'm going to solder everything haphazardly, because it's just an unimportant first prototype, right? Then I'm going to reconsider, because maybe this is interesting enough for a YouTube video after all. No kidding, I'm not sure how palatable this low-tech stuff is going to be after we've been looking at exciting lasers and powerful CNC machines. So if you have an opinion about this, let me know. Either way, this MSOP op-amp is not that critical. It only has to do the low-pass filtering at unity gain, far away from the things that usually give op-amps a hard time. Like nanovolts, high frequencies, or its power supply rails. I think I chose an OP2177 for this position. Or it volunteered, who knows. Unfortunately, resistors, capacitors, and all components in general are noise sources on their own. The circuit might not work that well without components though, so we've got to make the best out of it. First and foremost, at all temperatures other than 0 Kelvin, resistors emit thermal noise. That depends only on resistance value and temperature, so there's little we can do about it other than cryo-cooling. We can, however, reduce contact noise, which depends on geometry and composition. What that boils down to, essentially, is carbon resistors bad, no surprise there, and thin film and wire wounds good. In this area I'm using thin film precision resistors exclusively, and they are dirt cheap, so no problem. There's also shot noise, which depends on current flowing through a resistor, but there is hardly any current flowing here anywhere, so it shouldn't matter too much. So far, Miniware's new TS80P soldering iron has been doing pretty well for itself, in spite of lead-free solder and an unsuitable cone-shaped tip. But still, to clean up my poor manual soldering without stressing the precision parts too much, I'm putting the board on a 150°C hot plate and am pushing the joints over the edge of reflowing with a minimal amount of hot air. The TS80P is called that because it works with USB-C power delivery now, making it twice as powerful as the original TS80 and about half as powerful as their TS100. That makes it warm up a lot faster and allows it to tackle more challenging tasks than I would have dared approach with its quick charge predecessor. This EMI shield is still quite challenging though, both in terms of finger heat resistance and soldering iron power. Ow, yeah, getting hot. My friend Franz was kind enough to take some X-ray images of my favorite soldering iron tips, revealing what we already suspected while looking at the original TS80. Its copper tip is almost as large as those of the big boys. It's a heat reservoir that is charged off-duty and can be dumped all at once into a joint. That makes it perform better than I would have expected from purely looking at the 30-watt rating. However, large ground planes can still drain that reservoir quickly, and then it's hard for the heater to catch up. Obviously, the TS80P can't, and it isn't meant to replace a full-size stationary station. But I still like it as a clever little mobile tool for taking down to the CNC machine or elsewhere. These chunky BNC connectors are taking even the higher power paste cartridges a solid minute or so to bring up to temperature. So there's no shame in calling in a little help for a nicer looking fillet. Alright, now our low noise amplifier is approaching completion. All that's missing are 1 or 2 input caps. The ones for which Jim Williams used one of these hermetic tantalum cans. Unfortunately, I don't have any of those handy at the moment, and I'm not too keen on buying either. So let's see if we can get away with something cheaper. The main purpose for this input cap is to provide AC coupling. We don't want to amplify the entire 7 VDC in or whatever reference we are measuring by times 10,000. That would be pretty catastrophic as a matter of fact. We only want to see the nanovolt AC content on top. The capacitance value dictates which frequencies are attenuated how much. To let 0.1 Hz through, it takes a fairly large capacitance value of 1000 microfarad. Now all caps have leakage current, even the multi-$1,000 hermetic tantalum ones. We have to get rid of that by giving it a path to ground, which is what that 2K resistor is for. Careful though, even a super low capacitor leakage current, like 10 nanoampere for example, flowing through a 2K ohm resistor, will cause a 20 microvolt DC offset behind our input cap. There is no simple way around it. That offset voltage will get amplified by our high gain op amps. This gives us the criteria based on which we can select the input cap candidates. I need an extremely low leakage current. I need approximately 1000 microfarad. And I would like it to fit inside of this enclosure. Please. Uh-oh. Dexter, what do you think? Do we have any options left? It looks like we do, even though it has been a pretty dry year with too little electrolytes in the ground. I suspect that with twice our usual detection proficiency, we'll find some older plants though. Oh, we are on the right track. And score. Alright, now to desolder those without starting a wildfire. Ooh. Calling this relic an older plant is quite an understatement. This is a special find. Deserving of a little reward. The root of that cluster is actually a hermetic tantalum cap. What an unbelievable coincidence. Judging by their surface patina, I reckon these are at least 47 years old. They have a lower than specified capacitance, but otherwise they seem fine. More than fine. I only just learned about the supreme qualities of tantrum caps, other than being planned obsolescence enforcers. Leakage current, however, the property that I'm most interested in for this project, not that great. Originally, I had 5 of these vintage German hermetic tantalum caps. I let them all soak for 24 hours, and then I selected the one with the highest leakage current of over 20 nanoampere at 10 volt. For a happy little autopsy. As it turns out, these guys are actually made from many smaller axial tantalum caps. Some parameters like ESR benefit from this construction strongly. Overall leakage current, however, is the sum of all individual leakage currents, and that is meh. These are wet tantalum slugs though, just not as big as the few $1,000 parts. Here's another special capacitor which isn't native to Germany, unfortunately. It's a leaded 470 microfarad MLCC. And I actually had enough hope in this candidate to import a set of 2 for this outrageous price. Because how on earth could a solid-state ceramic cap have any leakage current at all? Well, after a similarly long soaking time overnight, the pure sub-nanoampere leakage results looked great. Unfortunately, there seems to be a major temperature coefficient. 1 or 2 centimeter proximity to my finger makes a major difference, be it a thermocouple effect or growing and shrinking of the ceramic layers. I wanted to give him a try anyway. For a one-off piece of test equipment, the price would have been tolerable, and the fit would have been beautiful. But with a shorted input, where otherwise I would expect to see my noise floor, it behaves like a slow roller coaster. Enough of this foolishness. I honestly expected microphonic pickup by those huge MLCCs to be a bigger problem. But I guess it's mostly just filtered out. Squeezing the enclosure, deforming the PCB and putting a force on the MLCC leads is very noticeable, of course. But I still think the roller coaster issue is a thermal one. Those chopper amplifiers are actually drawing 6 mA each, draining the round batteries I had planned before within minutes, and are turning that energy into heat, which goes along with air convection and all that kind of fun. Here's the solution to that input capacitor problem. It's a lot of normal aluminium electrolytic caps. As it turns out, their leakage current varies a lot. Out of approximately 30 1000 microfarad caps from different series by the most popular manufacturers, I was able to select 4 specimens with less than 10 nanoampere after 24 hours of soaking. The only pattern I was able to recognize is a dependence on voltage rating. The more distance you can put between your expected DC voltage and the cap rating, the better. For my primary interest in 7 and 10 volt references, 50 and 63 volt capacitors worked best, without becoming too huge or too expensive. When charging an electrolytic cap for the first time, it forms a thin, isolating oxide layer by means of anodization. That process stops itself very elegantly, just as the oxide layer's breakdown voltage reaches the capacitor voltage. Then, over the course of hours or even a day, that oxide layer gets polarized. That effect is called dielectric absorption, and only when that is done does the capacitor reach its lowest leakage current. Afterwards, whenever the cap is confronted with a different voltage, its carefully grown oxide layer and its polarization have to be reformed to some degree. That's an unavoidable inconvenience that will ultimately impact the way my LNA is used. By the way, if you don't have a nanoampere meter yet, you most likely do. In many cases you can just connect a voltmeter in series and measure voltage over your input impedance to get a good idea. Okay, so by selecting the best out of many, I got a good cap now. It's too big, but a revision 2 was already necessary before, because of 2 battery-related mistakes. I'll do that later though. This video is already way too long, and I want to finish it by showing you some results. There is no power switch yet, so I have to start the thing with 2 jumper links. Then it takes a minute or 2 to wake up, catch its breath, and reveal the most important parameter, its own noise floor with a shorted input. With a halfway open enclosure, it looks like it's in the 100 nanovolt peak-to-peak neighborhood. My scope probe setup doesn't let me configure such a high gain directly, so all readings have to be divided by 10. To test if the gain is correct and the filters are working, I'm using an arbitrary waveform generator and a 1 megaohm 100 ohm voltage divider. Well, we are breaching VNA territory now, but as far as I can tell with my simple tools, the gain indeed looks perfect between 0.1 and, say 8 Hz. And then we slowly start to taper off. That's about as good a filter response as I had expected from such a simple circuit. First, I'm going to try and measure 9 volt battery noise, because I'd like to use those as a power source for all the other candidates. There is a reason why these aren't our highest performance voltage references today. They have a significant temperature coefficient. I'm sitting perfectly still, trying not to breathe. But a gentle whiff of fresh air through an open window absolutely makes my readings plummet. Not sure if this is a meaningful measurement at all. I vaguely recall seeing some better results on the internet. This is a 7805 linear voltage regulator. An absolute staple to electronics everywhere and for as long as I can remember. In this test setup it's got plenty of high quality capacitance to support it. And it's fed from a ripple-free 9V battery. The caps I've used here exceed the datasheet recommendation by far. But it's great to see what a fantastic 0.1 to 10 Hz noise performance one can get from such a cheap and common part. Even more so under load. I'm genuinely impressed. This thing, the LT3042, is regarded as one of, if not the, overall lowest noise linear voltage regulator on the market. In the arcane arts of 0.1 to 10 Hz noise, however, it is not that great. They aren't boasting about it in the datasheet, so it's probably just not designed for that. I put it into an absolute shielding fortress to get to 10 microvolt peak to peak. We're homing into what started my interest in noise to begin with. Apart from this guy and his Mersbow posts on Discord. This LT1031 is a buffered, buried Zener diode-based 10V reference. And it's a straightforward sanity check for my preamp. It's good, 3 to 4 microvolt peak to peak, whereas the datasheet states a maximum of 6. Okay, now it's getting interesting. This is one of my 2 KX LTZ boards, the one that was powered on the longest. The one that brings back fond memories of the good times, where we had large public things like Maker Faire Hanover, where I had that reference measured at the stand of the Physikalisch-Technische Bundesanstalt. It's not doing well though, unfortunately. 20 to 30 microvolt peak to peak is at least an order of magnitude too much. That's what I get for treating that one with maximum care. I hope that's just a dead op-amp or the heater transistor, and not the carefully aged LTZ itself. Maximum care, maximum care, maximum care. This is the other bare LTZ board, which I've treated disrespectfully. Played around with, used as a video prop multiple times. Hell, I even touched it without gloves. But its noise looks almost good. It's configured for 5 mA Zener current, so I'm expecting no more than 1 microvolt peak-to-peak noise. With a minimum of thermal insulation. With a minimum of thermal insulation over the metal can, I'm getting that, and more. Yep, 800 nanovolt peak-to-peak noise, that's my high score for today. My setup has no magnetic or electromagnetic shielding worth mentioning, so that might be an opportunity for improvement. Honorable mentions. I don't think I've introduced you to the newest addition to my bench yet. For now, I hope it's sufficient to say that Advantest R6581T is also based on an LTZ. And its resistance measurement current is derived from it. So of course it's a great low noise performer as well. We could go all out and have the oscilloscope's FFT function calculate a noise power density spectrum. But I don't really see why right now, other than that looking really cool. Last but not least, the bench dominating, the almost bench breaking Fluke 5700A multifunction calibrator. Set to 10V DC, of course it performs precisely as predicted in their extended product specifications document. 2 microvolt peak to peak and some change. Holy moly, originally this video was meant to be about the TS80P. No idea how that could have escalated to 25 minutes of noise rambling. Well, at least I got that out of my system now. The preamp will come in handy soon. I'll fix the battery thing before committing it all to GitHub. Then it'll be buried underneath affiliate links in the video description. Alright, thanks for enduring. See you later.